So, welcome back friends. So, we were looking at interactions between electrons and photons, and we wrote down the first interaction with vector like interactions between electrons and photons, and then we nomenclatured the theory as quantum electrodynamics. It is perhaps the most popular theory of understanding in nature, essentially one of the most important theories. So, quantum electrodynamics continued. Okay, we are continuing the theory of quantum electrodynamics. So, we first wrote down the Lagrangian, and then we started deriving the Lagrangian in various cases by using symmetry arguments. We saw that the quantum electrodynamics Lagrangian has a global U1 symmetry or the arbitrary phase rotation symmetry. Similarly, it has a much stronger symmetry associated with the, and which can be argued for the introduction of the interactions itself, essentially by demanding a particular local arbitrary phase rotations. You end up having interactions input into your theory such that because you want to cancel the derivative, and the derivative comes make it into a covariant derivative at every space time point, and this will introduce you interactions, which is essentially the mu theory, mu with the photon field which we will introduce into the thing. So, let me just recap the Lagrangian of the quantum electrodynamics. So, you see it is better to put the I here. Okay. So, you see that minus 1 by 4 f mu nu f mu nu. Okay. So, you see that this is the Lagrangian given by this and well the D is del mu plus I e a mu, the photons essentially. So, we have seen two symmetries which are essentially the continuous symmetries, which are the global arbitrary phase rotations and the local arbitrary phase rotations. The local these symmetries come under a class of continuous Lie algebras, which we have seen when we are studying the Lorentz group a little bit more, and they come under this group called U1 group of Lie algebras. So, U1 group of Lie algebras, U1 is a unitary matrix of one element essentially. So, which is nothing but the phase. So, this is a local U1 group of Lie algebras essentially, which leads to this symmetry. Okay, this is just a nomenclature, and we have seen that this local gauge group fixes this Lagrangian for us essentially. So, this Lagrangian is fixed by the symmetry also, okay, in addition to the other symmetries which we demand, that essentially that the Lagrangian should be real, it should be Lorentz invariant, so it will be a Lorentz scalar and so on. So, the Lagrangian is manifestly a Lorentz invariant. Manifestly Lorentz invariant. Now, with this I can now what are the other symmetries? What are the other symmetries? The other symmetries are discrete symmetries. That the QED Lagrangian has. These are essentially so what are the other symmetries of QED Lagrangian, which are essentially okay. So, C charge conjugation, parity and time. So, these are essentially the discrete symmetries of the Dirac Lagrangian, which follow through for the also the QED case essentially. Okay. So, C is essentially the charge conjugation symmetry. P parity, T time reversal. Of course, given the CPT theorem, we know that the Lagrangian is CPT invariant because it is Lorentz scalar, real, Hermitian and local interactions. So, the Lagrangian is of course CPT, the product of all the three is the Lagrangian is also not just individual C, P and T, but also CPT products of these symmetries, variant and CP invariant. So, it has lot of symmetries. So, CPT, CP, CPT, Lorentz invariance and global gauge and local gauge, essentially this has lot of symmetries, this Lagrangian. So, with this reason it has interesting consequences. Good. So, now let us look at simple process in QED. Processes in QED. So, the simple process in QED, what before that I need to write down the Feynman rules of the QED thing. We will work in Lorentz gauge, we will quantize the mu field in Lorentz gauge and start working with it essentially. So, the basic idea is that work in Lorentz gauge, okay, and then write down the Feynman rules. So, there is a more general gauge which people use nowadays, which is called RZ gauges, which no, not nowadays, they have been using it for the last close to 40 years or something. So, we will come to RZ gauges a bit later on when we are dealing with these are more useful when you are looking at higher order process and just checking whether your results are complete, meaning the gauge invariance is preserved in all your calculations and the gauge and your results are gauge independent essentially, that should be the main. Then in those cases the RZ gauges are extremely useful. So, let us write down the Feynman rules. So, what are the external lines? So, external lines are your essentially the incoming electron and incoming positron. The incoming electron, okay, incoming, we start with the vertex and the incoming electron will give me a u of Ps. So, this is a spinor associated with the so this Feynman rule tells you that this should have a u of Ps, which is the spinorial index, the spinorial wave function which is associated with this. Incoming positron which is anti electron will have V bar of Ps. Okay. Okay. Then what about the photon? So, you can have photon also external, is a QED is a theory of electrons and photons. The electrons and photons, the photons also can have external lines. So, you can have photons. Now, photon it does not have electric charge, it is its own antiparticle. So, it does not make sense that antiphoton or photon incoming outgoing. So, incoming photon you can have the sign of the P if the photon momentum in this direction, essentially it is coming in this direction. So, it will have the polarization factor, again since we are using Lorentz gauge, it is a 4 component polarization wave function, okay, incoming photon with P and S essentially because we gave the direction the polarization vector is essentially a 4 component vector. In the Coulomb gauge is just a 3 component vector, if you remember. Okay. Now this is, now what about outgoing? Okay. So we finished the incoming lines. Outgoing will be essentially stars of these things. Okay. Outgoing electron. So we start with the vertex and it is going out, okay, electron. Then outgoing positron, so it has an opposite direction. And then outgoing photon, it has epsilon mu star of Ps with a momentum p, say for example, same thing. Now let us look at the propagator. So this finishes all our external lines. So incoming, because it is only a theory of electrons and positrons, electrons and photons. So when I say electrons, it also includes positrons also. So these are all the possible external lines you can have. Then we look at propagators. Okay. So the propagators are, so we will start with the electron propagator. So this is I, this is nothing but your plus m by p square minus m square plus I epsilon. This is the Feynman propagator associated with the electron field, which we had derived and seen, okay, already essentially. Okay. In that, when we are quantizing the Dirac field, essentially when we did the quantization of the Dirac field, we did. Then we have the photon propagator. Let us write it in Coulomb, not Coulomb, essentially in Lorentz gauge. So you see that I can write it down directly in terms of eta mu nu q square plus I epsilon. It is the Feynman gauge. Feynman. It is also the Feynman propagator and also the Feynman gauge, but I have not defined the Feynman gauge here, so it is fine, or maybe I mentioned it in the previous lecture or couple of lectures ago. So these are your propagators. Finally, we need vertices. So it is a very simple theory, QED, and it can be completely worked out. So you only have 2 particles and 1 interaction vertex essentially. So there is electrons and photons and 1 interaction vertex, and this interaction vertex does not depend upon the momenta, it is a constant interaction. So it only depends upon I e gamma mu. So there is a incoming, so p p. Okay, I just put in momenta at each vertex, but the vertex itself is a constant independent of the momenta. So you have this I e gamma mu. Okay, if it maybe it confuses, so let me just remove this momentum assignments for the present essentially. Okay, so we covered the external lines, the propagator and the vertices. So we have now the full technology required to calculate various scattering processes in QED. Now QED does not have any decays because the electron cannot decay into itself, and the electron cannot itself decay to photons. You can ask the question, how many electrons does the how many photons that the electron can decay to, because photon is a massless particle, so and electron is a massive particle. So electron can decay only into photons essentially. So I will ask you the question. So this is a homework question, and also it will appear, why does QED does not have any decays. Okay, the decays I have made and essentially is some electron going to 2 photons. Why not? Why is not allowed essentially? If it is allowed, why it is not, meaning is it seen? How will you calculate it? And if you have an answer, let me know essentially. Okay. So and this is a homework, and this will appear in your in assignments and everything essentially. Think about it. Okay, there are several ways you can answer this question. This answer has several answers. This question has several answers. So you can answer it at several levels essentially, from arguing from symmetry arguments, kinematic arguments, so and so many things essentially you can do it. Okay, good. So let us just assume that QED does not have any decays, so it can only have scattering process. So simple scattering process in QED. So standardly there are 5 simple scattering process in QED. Okay. So let us look at one of them, each one of them now, and then we will systematically calculate them in this lecture and the next lectures. And okay, and these calculations are important essentially, and one has to do them thoroughly, and these are the basic things what we should all try to do, and these are important. So let me list down at least 5 of this simple process which everybody should know in simple scattering process in QED. So the first one is called Bhabha scattering. This is E plus E minus going into E plus E minus. So E plus is a positron, this is an electron, positron electron. Second one is called a Moller scattering. This is E minus E minus going to E minus E minus. Third one so the first one is Bhabha scattering, second one is Moller scattering, third one is Compton scattering. It is E gamma going into E gamma, and then the fourth and fifth are pair production. That means gamma gamma going into E plus E minus, and the fifth one is pair annihilation. E plus E minus going into gamma gamma. Okay. So these are the 5 basic process which everybody should know essentially in QED. Okay. So what we will do is we will try to solve meaning first hopefully we will try to derive first we will start writing down the Feynman diagrams associated with each of these process, and then see what are the calculations associated with it, and try to write down the amplitudes at least for one of the diagrams in each of these cases essentially. So, the first one let us look at is Bhabha scattering. So, as I keep saying that we should always, whenever I am drawing Feynman diagrams, I should mention the time direction. Okay. So, let me take the time direction to be in this way, it is in the horizontal way essentially. Time. So, you can have the first diagram you can have is E plus E minus, this is the vertex. So, this is backward in time, this momentum is in this direction. So, P1, this momentum is in this direction, this is P2, a photon, and this is a positron, this is E plus, maybe I will draw a bigger figure. So, incoming positron this way, incoming electron this way. This is incoming, sorry, this is incoming, this has a momentum P1, this has a momentum P2. So, the incoming positron, it should have direction opposite to the direction of momentum. So, incoming positron, incoming electron E minus, a photon, then the same thing. So, you have an outgoing electron, outgoing positron. So, this is E plus, E minus, let me call it as P3, P4. Okay. Now, okay, let us, I want to decide, this is a time direction, right, essentially this is the time direction. So, how do you decide this, what is this channel? In this channel both the momentum are coming and adding up with each other. So, adding up each other for the exchange momentum of the photon essentially. So, both the incoming momenta are adding up with each other. So, this is called S channel process. So, what is happening in this diagram is that the electron and positron are coming in, annihilating and then going out essentially. Okay, they are coming in, they are annihilating into a single photon essentially, but this is a virtual photon. So, in this channel, so the electron and positron are coming in, their momentum are adding up and they are annihilating. So, this is also called the annihilating channel. So, the annihilating channel, this is a S channel process. S channel means the momentum. You remember that we have this Mandelstam variables S, T, U, each corresponding to one of the channels essentially. So, the S channel process is the one in which the momentum comes out, adds up and give you this particular thing. So, let me leave this space here, essentially we will come to how to work it out and everything. Okay. Is there any other possible diagram? Yes, there is a possible diagram, another possible diagram. So, the positron can, okay, so let us take electron, the electron can come and go, the positron can come and go, and in between they can exchange a photon essentially. So, again I will give you P1, P2, P3, P4. This is positron, positron, electron, electron. Now, here what is happening? The incoming, the exchange momentum of the photon which is being exchanged is the difference between the incoming momentum. or if you want P2 minus P1 or P3 minus P1. Okay. So, this is the incoming the exchange between these two is essentially difference between these two these diagrams essentially. Here it is P3 minus P1 this moment of this one, or P2 minus P4. Okay. This is called a T channel process. This is called a T channel process. Now, you cannot have a U channel process in this case essentially, because then it will violate electric charge and all kinds of things, because you cannot have an electron directly going into a positron and so on, so essentially. Okay. So, this is the two diagrams which contribute to the Bhabha scattering essentially. Okay. So, the Bhabha scattering is given by these two diagrams. Now, if you have okay, let us come to the scalar. Okay, these are the two diagrams of the Bhabha scattering. Now, let us try to calculate these two diagrams in some way essentially. So, okay, so let us calculate with, we start with the vertex 1 and then we go to the vertex 2 essentially. Let us start with the vertex 1. In the vertex 1 you have V bar which is coming with the moment of P1 as in spin. Let us not worry about the spins now. The vertex is minus IE gamma mu. Then incoming electron which is U, which is coming with an electron P2 as this entire thing is one block. There is a gamma mu here, then I need to suppress it with a gamma nu with a q square, which is the photon propagator. The proton propagator we said, because it is a channel process, q square is equal to P1 plus P2 square. Now, then there is the vertex 2 which we write it down. Okay. So, the vertex 2 has okay, U bar P3 S I E gamma mu gamma nu. So, we have these two components each coming from vertex 1 and vertex 2, and q square defined in terms of the incoming momenta in this case essentially. So, and this gives you the amplitude, this is essentially your Im, okay, the amplitude, and the amplitude times the phase factor will give you the total cross section essentially. So, we see that we can write down the amplitude very easily in this theory. Okay. We can write down the amplitude, and now let us do the same thing okay, for the T channel. So, here also let us write it down what is what essentially. So, here you have this vertex 1, this vertex 2. So, let us write down this outgoing momenta U bar P3 S minus IE gamma mu. Okay, this is U P1 S. Then again I have eta mu nu by q square, and then you have V of P4, or we can start with V bar of P2, this to be minus IE gamma. This indices have to be upstairs. Okay. IE gamma nu V of P4S, okay, and with the q square given by P3 minus P1 square. Okay. So, again we have this thing. Now, Okay. So there are various interesting things about crossing symmetry and so on. So in this case essentially, but in most of the QED process, but let us not worry about this thing right now. So what we have seen is that we could write down the amplitudes for the Bhabha scattering in this nice fashion essentially. So what we will do, actually you can simplify it much further. Actually if you do it completely, essentially that you can write it down in terms of these kinematic variables essentially, and it turns out that you can write it in terms of S and T or S and U, essentially it depends on S and U channels, and then you get in much simplified fashion of this relation essentially after you sum over all the spins and everything and good. Now let us move to the next one. Actually this is I think U channel, it is not T channel, this is U channel, yeah. Okay. Now let us move to the next one, which is Moller scattering. So the Moller scattering is nothing but E minus E minus going to E minus E minus. Now it is obvious that it cannot have S channel because you cannot have an annihilation diagram with this. So what you can have are T and U channel, no sorry, this is T. As you know that S plus T plus U is equal to 4m square. Okay. Now the T is given by this. Okay, let me write it down nicely here also. You have an electron coming in and another electron coming in, which exchanges a photon. So this we have P1, P2 outgoing, P2, P3, P4, and you have the same thing essentially here, and this is electron. Now you can write down the amplitude in exactly the same fashion what we have written essentially. So you can write so U bar P3, there are no S I E gamma nu U P1 S I eta mu nu by Q square U bar P4 S I E gamma nu U of P2 S. Okay. But is it the only diagram you can have? You can have, because they are same particles, you can exchange the momenta, the outgoing particles are exactly the same. Okay. So you can have an opposite thing. Okay, you can have cannot distinguish these two essentially. So you have electron going here, electron going here. So you have P1, P3, P2, P4 and a photon exchanged here essentially. So these are identical particles, all of them essentially. So you can think of, there is some symmetry with which you can write down the amplitude, where you exchanged this symmetry, there is something called the crossing symmetry, which I did not come to, but at some point I will come essentially, that you can see that if I exchange P3 to P4 and define here Q square is equal to P3 exactly P3 minus P1 whole square. Now instead I take the same amplitude, replace P3 and exchange it with P4, and Q square also will become P4 minus P1 square. You get the amplitude of this diagram. Let me call this as T channel, and this would be U channel diagram. So you get the amplitude of the first diagram, essentially the second diagram amplitude is same as the first diagram's amplitude, with P3 replaced by P4. Okay, good. So, but there is some interesting aspect of this. I like this Moller scattering a lot. Essentially, there is one interesting scattering. So, because we spent a lot of time talking about symmetries and so on, what happens if I have the same process? Okay, if I have the same process, replace it with positrons, what happens? If I replace electrons with positrons, okay, the amplitude will be written in terms of U has to be replaced with V's. Okay. Will have U replaced with V with the appropriate momenta and so on, so essentially. So, U of Ps will become some to be more accurate, it should be some V bar of Ps or something, okay, some wherever there is an appropriate thing, but it essentially ends up being wherever there is a U, you replace it with a V. So, the amplitude is fully given and the diagrams are almost the same. So, everything the diagrams look the same except the arrows are changed. So, you end up having the same amplitude structure, but whereas the electron wave functions are replaced by the positron wave functions. After doing, it turns out that after doing the trace sums, you know, summing over the initial states and averaging over the final states, okay. So, what happens if you do all that stuff? After doing all that stuff, the amplitude is exactly the same. Or amplitude, rather let me move the cross section. Is exactly as the same as what we get same as for the electrons. Okay. So, what is happening here? That means there is no difference if I replace in a given process electrons with positrons. Okay. In a given process like electrons scattering with each other, and if I replace with positrons, I get the same answer. The theory tells you their cross sections are exactly the same. Okay. So, Okay, it is not obvious at the first step because you are replacing u's with v, but when you then do all the spin sums and everything essentially, and you will end up having the same cross section essentially. Can you trace the reason for this? The reason is the QED Lagrangian, as we have said there are discrete symmetries, it is CP invariant, C invariant, P invariant. So, these invariants tell you that if we replace the particle with an antiparticle, the Lagrangian does not change. If you replace the particle with an antiparticle, the Lagrangian does not change, and the Lagrangian and the interactions does not change. So, particle antiparticle symmetry exists. Which is the C symmetry, charge conjugation symmetry, and we also need CP symmetry also. Okay, anyway, okay. So, can exist in QED, and this leads that electron process with electrons, and positrons have the same cross sections. Okay, very good. So, we have seen two of these main things essentially. So, before going to the next one, which is the Compton scattering, I will take a break, essentially I will stop here. Okay. So, and in the next class I will come back to Compton scattering and we will continue with that essentially. But what I want you to, these things will come in your exams essentially, the all these 5 processes will appear in your exams. I expect all of you to work it out completely, do the trace formula, get the cross sections. I will provide you the answers, the final answers, but all the intermediate steps have to be done by you people. Okay. Okay, then I will stop here and we will come back again to look at Compton scattering from the next class. Okay, thank you very much.